Okay. So we're going to do some evaluation for metrics. We want to say, hey, I classified this stuff. What's good? What's not? All right. So we have a few things. For the first thing, basically, that's talked about the most is precision and recall. Okay. And precision and recall, I'm just going to give you the definitions a little bit. This is like actually the Wikipedia page for precision and recall is really great. This is actually where this is grabbed from. But basically, you can kind of think, say, all right, I say, okay, what is, if you think of a binary, say, oh, is it true or false? Like, for example, is the person sick or is the person not sick? That's like the classic like classifier. And you say, okay, you want to see if someone is actually sick, you want to say, yes, you are sick. And if they're not sick, you want to say, yes, you are, or sorry, no, you are not sick. You want to catch those people. And that's respectively true positives. If you say, oh, you are actually sick and you said you're sick. And then you're not sick, true negatives. And you said, oh, you're not sick. But sometimes you might classify saying, oh, you're not sick, you're okay, and then you actually are. This would be a false negative. And then conversely, if you say, oh, you're sick, but you just had like allergies, that'd be a false positive, okay? So this allows us to basically break the parts into those four parts, and we can actually build into, for example, precision and recall. And these are actually really, commonly used, basically saying like, okay, what's the importance? In this case, precision, it's just saying all the true positives divided by all the selected positives. So if you imagine this is all the selected positives right here. This is one that we said they're all positive, and these are basically the fraction that were actually positive. And then recall is basically all the true positives, with all the actual positives. So these are all the actual positives. Maybe you got some wrong beginning that part. And it turns out that precision and recall actually kind of fight against each other. They kind of like are opposite of each other. Like if you get really high precision, you'll have poor recall. If you have good recall, you'll have poor precision, okay? So the way you can kind of think of this, like high recall, basically it's like, okay, high recall means like, oh, we want to make sure we capture all of the positive stuff. So if you didn't know anything, you would just say everyone is positive. Okay, you would say everyone is sick, because then you would know for sure you got everyone who is actually sick, right? So this recall would be 100%. This value would be completely taken up, okay? But, so kind of graphing it out or drawing it out a little bit, this would be saying, all right, if I say all of these, everyone is sick, I would get 100% recall, right? Because this would all be my true positives. And these are all the selected positives. So like, cool, okay, high recall. But the problem with this is that now I said people who were not sick were actually sick. Or sorry, the ones who were not actually sick, I said, oh, you're sick. So I have a lot of false positives, okay? So that's where basically this comes in to say, well, if you have a lot of false positives, this ends up being a very low precision. And then the opposite of this is say, okay, let's do high precision. Say, I don't want to make a guess only if I'm near 100% certain. So like maybe you basically say, I don't want to say someone's sick when they're not actually sick. So the extreme case is saying no one is sick. But let's say we say, oh, this one person is sick because they were really, really sick. And you're like, I guess they're sick. But now you can see you missed a whole lot of actual positives here. You basically didn't get any false positives, but you got a whole bunch of false negatives on the side here. And you did get some true negatives, but this is where basically it's at odds. And so just kind of know that that when you do our precision versus recall, they're conflicting, and you have to decide, what is more valuable. Is it better to be more precise, or is it better to have more recall? And it depends on the situation. Sometimes, if there's like cancer, or let's say like some really, really bad disease, you might be like, I want to make sure we are certain for this disease. And so you might have, for example, very high recall. You want to make sure that you get all the positives that are positive. Now, the problem with that is like you might get someone saying, oh, like you have this deadly, deadly disease, but they don't have it, but maybe you're okay, making that assumption. No, that's not actually true how medical doctors will do things. They'll say, oh, wait, we need to, we need to make sure we don't cause more pain for someone who doesn't have the disease. Basically, don't do extra tests or make them freak out because they think they're diseased, okay? So just know that part, it's like conflicting back and forth. And then one other thing, another metric is accuracy. So this is one that's usually talked about the most for like as a metric, is saying like, oh, okay, you know, what is a good classifier? And it's just the true positive plus the true negative divided by all the observations. So you can just think it's like, okay, like how many did I get right here? How many did I right here versus all of it? This is probably like the simplest one. If you wanted to say accuracy, you probably would have done this like by nature. So this tends to be commonly reported. But there's another one called the F score or F1 score. And the F1 score basically says, hey, all right, how basically does a balance between precision and recall. And this allows us to basically do what we call like a harmonic mean or harmonic average. And basically it punishes where like if you did something extreme where you're like, oh, all of these people are sick and you have a high recall, but a low precision. And so basically, oh, I don't know why I messed this up. Sorry guys, this is gonna bug me if I don't fix it. Okay, so, close enough, okay. So we have our F1 score here, and basically it's 2 times precision times recall, and then precision plus recall. So you can sort this out, but basically this is kind of like saying, okay, precision and recall are equally important. So a mid-range of precision and a mid-range of recall is a good value, basically. Okay, so this is great when you have you want to have a good balance for precision and recall, but let's say you want you want more precision or more recall for your situation, you can use an F beta score. So this is actually talked about in the curriculum, but this is something you can do. Basically your F beta score, okay, essentially you have that same thing, but you have, instead of just a 2, you have a factor in front here, 1 plus beta squared, and then divide by beta squared here, where you times by the precision right here, okay? So note that, for example, F1 is basically a special case of beta. Usually we'll see like F.05 or what's the other one? F2 scores. You'll sometimes see those kind of things depending on if there's more precision or more recall focus. Okay. All right. Any questions about metrics, just in general, of how this works or anything like that?
What did you say the beta number is exactly?
The beta?
Yeah.
Yeah. Basically, it's just saying how much do you prefer precision over recall? That's essentially what it's doing. It's there's no like, it's kind of just like saying it's a weight factor. So instead of like the harmonic mean basically makes them balanced, the beta factor allows you to say, oh, I really care about precision, or it's like, I don't really care about precision that much.
Okay, so like I don't know, a 0 is like I don't care about precision, and what would be a high number for a beta thing?
Yeah, you can have as high as you want. Usually 0.5 and 2 tend to be that range. You could go higher or lower. The lowest obviously you can go is 0. That's the extreme value. The highest value you could do is like infinite precision, which doesn't really make much sense. But like usually you would have between like 0.5 to 2. I don't think I usually see anything bigger than that.
Okay, that makes sense.
All right, cool. And this will lead us to confusion matrices. All right. So confusion matrix. So basically, it comes down to the fact that confusion matrices, and you'll see this a lot, is that you will see type 1 errors and type 2 errors, basically false positives, okay? How many false positives you have and how many false negatives you have, okay? So you can, I won't go in the whole like, you know, type 1, type 2 error. You can probably look that up or kind of figure it out, but just know that's what that means, type 2 versus type 1. So a confusion matrix allows us to actually figure out these false positives, false negatives, and true positives. So I'll show you an example of confusion matrix in a second, but basically it comes down to diagonals are true positives, and the y-axis is the true label. So I have an example here from a paper I was reading before. I'm just doing this from familiar. So this actually, this I'll show you guys in a second. Basically, this paper talked about trying to detect American Sign Language with using letters. For example, this is an A, this is a B, this is C, the D, E, F, you know, and so on. So basically it's like, okay, here, right here is saying, all right, this is what the value actually was. It was an actual A, okay? And it was predicted to be an A 75% of the time. It was predicted to be a C 0.05 or 5% of the time, M 5% of the time, O is 5% of the time, and so on. And so you can see here it's this diagonal. This is usually how you'll see a lot of fields show these values. Sometimes it's percent, sometimes they're just numbers. And this diagonal right here are basically true positives. And if you read it from the right to on the horizontal part, you can say, oh, these are all false negatives, basically saying, oh, it was an A, but it said it was a C. Okay, if you read it downward, you would say, oh, these are all like false positives, where it says, oh, this is a C, but it's not a C. This right here is my true positive. So I just wanted to show you guys another example. There's one in the curriculum, but wanted to show you guys that one. Okay, so here's a couple examples from the curriculum. The simple one is just, there's two classifications. You either have a true or a false one right here. So the label is 0. So this is the actual label, and this is the actual label, and this is the predicted label. So the actual label for these values were 2. There were 5 zeros. I'm sorry, the actual label was 0. There were a total of 5 that were actually labeled as 0, and it predicted one of them or 2 of them correctly as 0. But 3 of them, even though they were labeled, they were supposed to be 0, it was predicted to be a prediction of 1. Okay, and same thing right here. So this is a very simple one. This is from the curriculum that shows you how to make this. Notice that one thing in here is that it's a heat map. And so basically very high precision, or it's not high precision, basically high values will be coded, in this case, darker. Usually, I mean, this is like, I don't know. I see this a lot with like smaller data sets, more on the medical field, especially in this way. I don't like this as much. I think percents make more sense, but that's just me. But just know this is just basically which one you're catching. So you can also do this with multiple classes like I showed, if you have multiple labels and seeing what this is. And you can see right here, oh, that's a pretty good job predicting this stuff, and they have a few false positives or false negatives, depending how you look at it, okay? So I did want to show you a couple examples how this can get really complicated. So this one, I think, I like doing this. This is actually a project I've done right here. None of this is not up right now. I had to take it down for a couple reasons. I need to fix some issues with the data, and I didn't want to put out that information, have people confused. So I needed to fix that. So just know if you try going here, it will also private, but that should be up in a few bits. So you can see here, basically it's predicting sign language. So like, is it an A, a B, a C, a D, an E, an F, right? And so on. And so you can see right here is that these are all the true labels, and these are the predictions. So A, it got 82% of the time correct. And you can see sometimes, like for example, on this darker spot, 25% of the time, if I go down for this very big part, it thought it's a T, which actually makes a lot of sense. So for example, this is an A in American Sign Language, and this is a T in sign language. So you can see that in ASL, A and T look very similar. So you would actually expect that to actually be that very similar, what's it called, like guess wrong. And so you can see that's pretty big. And you can see there's a couple ones, like this one's, let's see if let's see, M and M, it's a good one. So you can see 45% of the time it guessed M correctly, and the other times mostly it was N. So this is the letter M in American Sign Language, and this is the letter N in American Sign Language. So this is a very subtle difference. So you can see like where those errors come from. And you can see something similar here. This is a G, this is an H, and that's where this part comes over here. There are also some random ones here. For example, this S right here is labeled as E, which this is an S and this is an E. So maybe there's some distinction right here. So no, and these are from 2 different models. So for example, this is from a prediction model called VG16. And this one right here is from ResNet 50. And you can see that depending on the model, it does worse or better. So you can see there's a lot less false positives over here, okay, for a lot of these things. But there's some that are much stronger. For example, this is a smaller percentage over here. So this allows you, instead of declaring like the whole thing, and saying how good was your precision and accuracy, you can say, oh, wait, let me look at specific classified labels and stuff like that. So that kind of gives you an idea of things. And let's see here. I think I have it on this paper. So you can see these are some of the images that we're trained on. So you can see like this is a U, this is a G, this is an X. So you can see there's an M. So you can see this is what the computer's looking for. But I wanted to show you some things you can do. So you can start saying, okay, like you start seeing patterns. For example, say, oh, here this M and N are very close together. This T and let's see here, I think is this S and T? Yeah, S and T are very similar. This is S, this is T. So you can see they're very similar. That's a lot of confusion parts. And you can see I compared the other models, like, well, this other model here, there is still confusion here, but you can see that it does a little bit better. Orange means better values, like it did a better job prediction. You can see that many more of the values are actually orange in this case. Okay, so you can kind of do some quick comparisons for different models and how well they predict things. You can see here's the different letters, like A, M, N, M3S27. So I'm kind of giving some context of like how you would use these confusion matrices and what kind of insight that would give you. All right. So that's all I had to say about for confusion matrices on this part. You guys have any questions?
No, thanks. That was interesting.
Okay, cool. Thanks. Yeah, and again, confusion matrices. I think people forget to use them more often. I think they're actually really, really useful. And again, like I think I've told you guys like 100 times now, it's that in data science, like you as the person give a lot of insight and be able to look at something visually and very quickly seeing like, hey, like, you know, what parts did it do really well and things stick out. For example, that 0.25 over here really sticks out to me, or the fact that there are some letters that are very similar together. So you can do some very quick comparisons, very quick analysis, and then you can investigate further and say, does this make sense? So useful to know.